Welcome to bonding in heteronuclear diatomic molecules. So here we still have a diatomic molecule, it's still only two atoms, but now we have molecules, we have two atoms that are not homonuclear, they don't have the same nucleus anymore. Now they have two different nuclei, we have two different elements that we have bonded together. So now we're going to have a polar molecule. So let's look at an NO molecule. So this has 11 electrons. So note that now we have an odd number of electrons. We have 5 valence electrons from nitrogen, 6 from oxygen. And if we place these electrons into our molecular orbitals here, into the molecular orbitals that we expect for the homonuclear nitrogen or oxygen molecules, we get the energy diagram that we see over here. So note here that now we have an odd number of electrons. We have 11 electrons here. We have 1 electron in the pi 2p star orbital. And so now the bond order is 8, because we have 8 bonding pairs of 8 bonding electrons. We have 3 antibonding electrons, and we divide by 2, we get a bond order of 2.5. So now we're able to talk about molecules that are radicals. They have odd numbers of electrons. And so now we can explain this using molecular orbital theory, but we would never be able to explain that using the localized electron theory, because the localized electron theory deals with pairs of electrons. We don't have to deal with pairs of electrons anymore. So now let's look at hydrogen fluoride molecule, HF. So the atomic orbitals of hydrogen and fluorine are at significantly different energies, with the fluorine orbitals significantly lower in energy because of the significantly larger number of protons in the fluorine nucleus than in the hydrogen nucleus. So note here that the 1s orbital for hydrogen is higher than the 2p orbital for fluorine is. So this means that when we mix the two together, the molecular orbitals will have, one of them will have a greater electron density near the fluorine, the other one, the antibonding orbital, will have a greater electron density near the hydrogen. And so, of course, the one near the fluorine will be more energetically favorable. So if we move the electron down from each of those, that's going to be where the electrons are going to want to reside, so closer to the fluorine, which means that now we're going to get a case like this, where we have more of the electron density shifted to the right near the fluorine than we have over near the left. If we do the opposite, then the fluorine is going to say, "Nuh-uh, I'm out of here," and it's going to tend to leave. That's why it's an antibonding orbital. But the bonding orbital has more of the electron density pulled towards the fluorine atom, which means the hydrogen side of the molecule is going to have a partial positive charge. The fluorine side of the molecule is going to have a partial negative charge. So if we look at other heteronuclear diatomic molecules, we'll have a similar asymmetric molecular orbitals, with the bonding orbitals having more electron density near the more electronegative atom, and the antibonding orbitals having more electron density near the less electronegative atom. So that was bonding in heteronuclear diatomic molecules.